Hi, and welcome to the talk A Separation Logic for Effect Handlers. This is joint work with François Pottier. So we are going to start the talk with a brief reminder of what effect handlers are. In a sense, effect handlers are a generalization of exception handling, and we are going to understand that by comparing two examples, one written in OCaml using exceptions and the other written in multi-core OCaml using effect handlers. We define an exception division by 0, and then we define the division between two integers x and y. If y is equal to 0, we raise an exception. Now we can try to execute an arithmetic expression, and if we raise an exception, the whole computation will be discarded and replaced with the exception branch. Now, with effect handlers, we start pretty much in the same way by defining the effect division by 0. Then we define the division between the integers x and y, and if y is equal to 0, we perform the effect division by 0. We can also try to evaluate an arithmetic expression, but the difference now is that if we hit a division by 0, instead of discarding the whole computation, it will only get paused and will be represented by this value k, which we call the continuation. To resume the computation that was paused, we call this continuation with an argument that will replace the division by 0. Since here we call the continuation with the argument 0, the expression will be replaced to 1 plus 0, which evaluates to 1. We could choose not to call the continuation, in which case the computation would be discarded and the dynamic behavior of this code would be similar to that of exception handling. That's why effect handlers generalize exception handling. A well-known application of effect handlers is the implementation of a memory cell which we can access through effects get and put. We are going to see this application as a motivation for our search for a way to prove the correctness of code exploiting effect handlers. Here you have the effects get and put, and we notice that they have an arrow type. Get has the type unit arrow int. This means that when we perform the effect get, we must multiply it with the value unit, and we can expect an integer in return. That's because in order to call the continuation, we must provide an integer, and that's the value that we get in return from performing the effect get. The same reasoning applies to the effect put. A program that performs these effects is what we call a client of get and put, and we cannot simply execute this client because we need to handle the effects it might perform. So that's what the function run does, and the idea here is to use a reference as a way to keep track of the state and answer the requests of the client concurrently. If the client performs a get effect, we are going to read the reference and call the continuation with this reading. If the client performs a put effect, we are going to first update the reference and call the continuation with unit. In the third branch is the case of normal termination of the client, and in this case we are going to simply replicate its output. Now we can try to see if this implementation does work by defining some clients and making some dynamic checks. For example, here we have two simple clients that simply perform the effects. With these functions, we could build larger clients by composing them. Then we can make the check, and hopefully it would return true, and indeed it does. So apparently it seems correct. But up until now, there was nothing exciting. But because effects are detached from handlers, we could try to implement this memory cell in other ways. For example, we could try a pure implementation. And as we're going to see, this implementation does exist. But it's much more involved than the first one. There's no problem if we don't understand it at first. because the purpose of showing this implementation is exactly to prove a point that reasoning about effect handlers sometimes is hard. So here is the implementation, and the strategy is to transform the client into a function that takes as its argument the initial state of the cell. If the client returns normally, we are going to simply ignore the state. If the client performs a get effect, we are going to continue the client with the current state, and if it performs a put effect, we continue with the value unit. Then we execute this function by applying to 0 the initial state. We can also make a dynamic check, and it also seems correct. But of course, these dynamic checks are not sufficient to establish the correctness of these implementations. So an important question is how to verify that they are correct. We might argue that for the first example, we don't need to do it because it is simple to understand. But as we saw, that was not true for the second one. And there are even trickier examples, such as a library for asynchronous computation using effect handlers. We see that its implementation uses a number of ideas, such as mutable state in the form of cube and references, and of course continuations due to effect handlers. Another question is, how can we specify effects in handlers? It would be useful to have a specification of a handler and then prove that both run and run prime are handlers for the same set of effects. And finally, a third question would be how to reason in a modular fashion about client and handler. So given some clients, for example these two, we would like to say in a way that they compute the number 2, but as we know, without a proper handler, they do not even can be executed. In this work, we are going to answer these questions by devising a novel separation logic. A separation logic where we can both specify and verify programs exploiting effect handlers, and we can do it in a modular way. So we preserve local reasoning from standard separation logic. That means in a verification task, we don't need to reason about the global state. We only need to reason about the resources a program uses. And we can reason about client and handler in isolation. In this talk, we are going to first see how we did that, what was our plan of attack, and then we are going to see some details of the logic. First, the novel idea of protocols, and then we are going to see how can we reason about client and handler within this logic. This is the footprint of our work. Our idea was to couple iris-based logic with a programming language with support for effect handlers, and then derive the separation logic. Iris-based logic, it's a modal logic with some standard modalities such as the later modality and the persistently modality. And a separation logic is where we can reason properly about programs with notions such as hard triples and reasoning rules. And the whole was done with think-off, which says that everything was formalized and verified by the machine. Now, the additions of ours in this scheme were the programming language and the separation logic itself. The programming language, which is a lambda calculus with recursion references and effect handlers, and the separation logic where we have this novel notion of protocols to account for effect and their handlers. A protocol is simply a way to describe the interaction between client and handler. What do I mean by interaction? We are going to see that with an example. Let's recall the effects get input, and we imagine that we have client and handler implementing a memory cell initialized with 0. The client may perform the effect put1, which you can see as sending a message to the handler. The handler updates the state and eventually continues the computation of the client. This we can see as a reply to the message of the client. Later on, the client can perform other effects such as the get effect. And we can also see it as sending a message to the handler. The handler receives the message and replies to the client by calling the continuation with the reading of the current state. And that's what I meant by interaction between client and handler. So from the eyes of the client, performing these effects were pretty much like function calls. You could imagine that he was simply manipulating a memory cell. And from the eyes of the handler, he could understand this interaction as providing a service, the implementation of a memory cell, and answering to requests sent by the client. So the protocol will describe this interaction and enforce that both client and handler agree on this interface. How can we write protocols? One way of writing protocols is to say that the answer to the message at V is the value W. But since we aim at a separation logic, it makes sense not to send only values, but also send resources. So we add the propositions P and Q to this syntax to say that if the resources described by the proposition P are sent, then we can expect the resources described by Q in return. Another way to write protocols is by the sum of two protocols. And intuitively, it means that we can either agree with the protocol on the left or that on the right. And finally, there's a third way to write protocols, which means that there's no interaction between client and handler. Therefore, the client is a pure computation. A small issue with the syntax of protocols is that the values V and W and the prepositions P and Q are all fixed. So what we do to add some flexibility to the syntax is to add binders. Now they are open terms with three variables bound by X and Y. The intuitive reading is updated to say that the client can choose how to instantiate X, and similarly the handler can choose how to instantiate Y. Let's see an example of a protocol. So consider the effect ABORT, and from its type we notice that it behaves like an exception. We can always perform the effect ABORT, but it can never returns. So interaction only happens one way, from client to handler. And what would be the protocol of such an interaction? So if you want to figure it out by yourself, feel free to pause the video while I give you a couple of seconds. Congratulations for those of you who have tried. And here is the answer. The protocol basically reads as we can always perform abort, because then we would only have to prove the proposition true, which trivially holds. But we can never return, because to return we would have to prove the proposition false. What about the effects get and put? Well, before we move into that discussion, let's see how we write the specifications of the functions get and put in standard separation logic. Here, S is a predicate satisfied by the current state of the memory cell. The specification of get reads as if before the state is X, then afterwards the state is the same and it returns X. The specification of put says that if the state is X, then afterwards it is updated to Y and it returns unit. Now let's move on to the protocols. So the protocol state is a sum of the protocol get and put. It reads as we can either perform the effect get or the effect put. The protocols get and put are similar to the specifications of the functions get and put and read basically in the same way. Protocols were only one ingredient to derive a separation logic for effect handlers, but we still need to tie it to the operational semantics of our programming language and to our base logic. In standard separation logic, The way we type programs to the base logic is by means of this construction called the weakest precondition. The reading of a weakest precondition is to say that the program E is safe to execute. It either diverges or reduces to a value V that satisfies the postcondition. So what we do is to include the notion of protocols in our construction of the weakest precondition. Now, a program safe to execute not only diverges or reduces to a value, but it can also perform an effect according to the protocol psi. A weakest precondition statement is going to be used as the specification of a program, and reasoning rules as ways to derive it. So standard reasoning rules found in separation logic are, for example, the rules value and step, which here are adapted to our system. The rule value justifies why a program that terminates is correct, while the rule step can be used to prove the correctness of divergent programs. Some reasoning rules that are unique to our system are the rules effect empty and the rule effect choice. The rule effect empty says that we cannot perform an effect under the protocol empty, because this would be equivalent to the proposition false. The rule effect choice says that if we perform an effect under the protocol sum, we can either agree with the protocol on the left or that on the right. Another reasoning rule is the rule effect, and it says that if we perform an effect under the explicit writing of a protocol, we must agree on the arguments and we must prove that the proposition P holds. Moreover, we must prove that under the assumption of the proposition Q, we are able to continue. And here I would also like to discuss a technical detail, but it's still important, which is that we do not include a persistently modality. So that means a continuation can only be called at most once. And here is where we choose to forbid multi-shot continuations, continuations that can be called more than once. Using these reasoning rules, we could, for example, prove that the program perform abort satisfies this specification. And the specification basically reads as we can never return because the postcondition is false. The rule we use to derive this specification is the rule effect. Also, we can derive the specification for the program perform get and perform put. And we see the similarity to their equivalent in standard separation logic. The rules I have shown so far only apply to simple programs, and we would like to be able to derive specification of larger programs from simpler ones. For example, given the specification of a function, we would like to prove the correctness of a program that calls this function. In standard separation logic, we do that by means of the bind rule. But there is a problem, which is if we try to adapt this rule as is into our system, for example, only by adding protocols at all the occurrences of the weakest precondition, we would get an unsound system. And that's because admitting this rule would be similar to admitting the equivalence between a handler and a program where we pull out the expression from the handler. And of course, this equivalence is incorrect. We found two solutions for this problem. The first solution was to impose a restriction on contexts. The rule only applies to contexts that do not include handlers. The second solution was to impose a restriction on programs. The expression inside the evaluation context must be a pure computation. And a remark is that both rules are valid in your system. Another important rule in separation logic is the frame rule, and it says that if a program doesn't use the resources described by a proposition R, then these resources remain accessible all along the execution of this program E. We can adapt this rule into our system as is because we made the restriction on multi-shot continuations. An important rule remains to be discussed. the reasoning rule to derive the correctness of an effect handler. So what would be the hypothesis of such a rule? Our idea is to concentrate all the complexity of this rule into one proposition, what we call the handler judgment. We notice that the handler judgment allows us to pass from one protocol to the other, from the protocol psi1 that describes the effects performed by the program E, to the protocol psi2, which describes the effects that the effect handler itself might perform. The handler judgment is the conjunction of two propositions, one dealing with the return branch and the other dealing with the handler branch. For the return branch, it basically says that the return clause is safe to execute for every possible output of the program E. Moreover, the return clause can perform effects according to the protocol psi2. For the handler branch, it's a little bit more complicated, but let's study it by parts. We see that it ends with the specification of the handler branch, saying that it's safe to execute, and we have an hypothesis which basically means that X is a valid argument of an effect performed under the protocol psi1, and K is a valid representation of the computation that performed that effect. So together, it basically reads as the clause H is a correct handler of any effect performed according to the protocol psi1. There is also a small technicality I would like to discuss, which is the fact that the handler judgment is a recursive definition, and that comes from the fact that handlers themselves are also recursive. The operational semantics of recursive handlers is known in the literature as deep handlers. We have all the tools to carry out the formal verification of our introducing examples. The function run can be proved to satisfy this specification, which reads as saying that for every valid client, run client is a program that does not perform effects and reaches the same pass condition as the client. A valid client is one that satisfies the highlighted proposition. We notice that the implementation of the state is abstract because of the universally quantified predicate S, and that the client can only access this state through effects get and put. We also notice that the initial state is 0. In order to derive this specification, we would have to apply the effect handler rule and then prove a handler judgment, and at this point we notice the choice of implementation for the state. We also notice that the handler will allow us to pass from the protocol state to the empty protocol. And what's also interesting is that the same specification is satisfied by the pure implementation of run. And now we accomplish our goal of proving the same specification for both implementations. We have reached the conclusion of the talk. What were our contributions? We have introduced a separation logic for effect handlers with this key idea of protocols that enables modular reasoning about client and handler. We also preserve some other forms of modular reasoning, such as local reasoning from the frame rule. And all of that was formalized in Coq. There are some topics in the paper that didn't make to the talk, for example, the formal model of the logic and the treatment of shallow handlers. Here in this talk we saw deep handlers, but in the paper we treat both. There are also the formal verification of libraries using effect handlers. There is a library for control inversion, and there is a library for asynchronous computation that we verified in the paper. What are some limitations of our work? One limitation is that we do not have primitive concurrency. We think that we should be easy to address, but we don't have at the moment. We also didn't figure out yet how to conciliate both multi-shot and one-shot continuations in the same system. Moreover, there is a simplification in our semantics where effects are always caught by the nearest enclosing handler. And that's of course a simplification that we would like to address. So that's the end of the talk. I hope you have enjoyed. If you have questions, please ask them during the conference. And otherwise, I'm going to say thank you very much for watching and bye bye.